In this part, we will discuss the topic of marginal probabilities and joint probabilities. I'll tell you what that is in a second, but part of the reason is that I'd like to get to the interesting topic of drawing samples from a Gaussian probability distribution, or normal, which requires that we first introduce the concept of joint and marginal distributions. So we can ask ourselves the question, what is a joint distribution? Well, when we have distributions that depend on very many variables, the joint distribution is a distribution on all of those variables. So for example, if I were to write down a density on R1, R2, this would be an example of a joint distribution. While a probability distribution in P of R1 or a distribution of P of R2, those would be examples of marginal distributions, distributions that depend on only one variable. In fact, as I'll show shortly, we can obtain the marginal distribution, sometimes simply called the marginals. We can obtain the marginals of R1 and R2 from the joint distribution P of R1 and P of R2. So when we speak of joint distributions, we can sometimes say that R1 and R2 are drawn from a distribution that depends on both R1 and R2. Now suppose that R1 and R2 are independent random variables. What do we write then? Well, we already know, sort of intuitively, but we can write down mathematically, that if my random variables are independent, then I can rewrite this joint distribution as a product of two distributions. So for example, what is the probability of drawing a cell of a certain size? And if I consider a completely, a cell from a different culture, I can say, well, what is the probability of drawing that cell of a certain size? Now, if those cells are not communicating with one another, if they're independent, and if they're the same type of cell, we would normally say that the probability of drawing a cell of a particular size and another of a different size is simply the product of the two. This is only true for independent probabilities. Of course, we can say the same thing for two independent dice or two independent coin flips. What is the probability of getting heads on this coin and tails on that coin? Those would be the product of probabilities because those probabilities are independent. Now, if those probabilities are drawn from the same distribution, in other words, the cells, like I said, are of the same type, then we would sometimes say that these are identical independent probabilities, and that our draws, and sometimes people use this fancy word, are IID. IID meaning identical, independently distributed. Now, it's not true in general that things are identical and independently distributed. You could be identical without being independent, or you could be independent without being identical. There's a special case of variables where you can write down probabilities as products of all of the same forms of the p's, which is a special case of identical and independent distributions. So this is normally how we would write something like this when our variables are, and I'm going to use that word, IID. Now in general, if the variables are not IID, and in particular if they are not independent, then I cannot simplify this P of R1 and R2 as simply the product of R1 and R2. I can't do that. Let's talk about how we get from joint distributions to marginal distributions. So again, P of R1 and R2 is our joint. And suppose we consider one of the two marginals. Remember, marginal is shorthand for marginal distribution. Let's consider that P of R1. How do I get from P of R1 and R2 to P of R1? Well, I would have to integrate P of R1 and R2 with respect to R2 in order to get P of R1. The process of integrating over R2 sometimes is given a specific name, and it's called the process of marginalization. Marginalization. So in other words, going from here to here is called marginalization. Sometimes people use the fancy word of going from here to there as the process of marginalization. So that's used a lot less often, and that concept will pop up later in slightly more technical settings. So for the moment, at least for the first half of this class, we'll primarily be concerned with the process of marginalization, going from multivariate distributions to single-variate distributions. Let's interpret this statement here in plain language to make sure that we understand what this means. Suppose P of R1 and R2 is a probability that it rained today. So this is the variable that coincides with raining today. And this is rain tomorrow. And I'm only interested in the probability that it rained today. So what am I doing here? What I'm basically saying is, irrespective of what happens tomorrow, I would like to know what happens today. So irrespective of what happens tomorrow means summing over or taking a sum over every possible outcome that can happen tomorrow. I would like to know what happens today. And this is how I would write these probability distributions. Now, same thing goes for the more complicated case. If I have D of R, now let's use fancy notation, 1 to 3, and I have a P of R 1 to 4. So this is a joint probability that depends on 4 random variables. Then here I will have P of R4. I will only be left with the fourth one. Now, I don't just need to integrate them in order. I can also say, well, I'm interested in the marginal over R2. So then I would integrate R1, and then I would integrate R3 to 4 of P of R1 to 4, and that would be P of R2. So this is, again, the process of marginalizing over 1 and variables 3 to 4. So at this point, we're ready to talk about how to draw samples from a Gaussian, because that will require 2 IID Gaussian variables. So and I alternate between Gaussian and normal, but technically the word normal is more appropriate. So drawing samples from a Gaussian or normal. So we remember when we integrate a Gaussian, it's a little bit complicated. Let's forget about the more complicated task of drawing samples from something, but let's even think about the very simple thing involved in integrating a Gaussian. Remember that when we integrate a Gaussian, not so simple, so we have to turn it to polar coordinates. And then we compute sort of the integral squared. What we find when we convert a Gaussian to polar coordinates and multiply it by itself, so we take the Gaussian integral, we square it, and then we convert the squared integral into polar coordinates, that we can then do the integral over the angle and do the integral over r. And then we get an answer, and then we take the square root of that, and that becomes the answer to our Gaussian integral. So by exact analogy, our sampling will also require that we take the probability distribution, square it, then take a random draw of the radial coordinate, take a random draw of the angle, and then convert those back into random draws of x and y, or the random variables directly from the Gaussian. So we will consider two random variables that are IID and drawn from a normal distribution with a mean mu and a variance nu. Now, if I were to write down the probability density, I would write it out as 1 over square root 2 pi nu e to the minus x minus mu squared over 2 nu. And remember, these are IID, so the probability of x and y is simply the probability of x multiplied by the probability of y, which is 1 over square root 2 pi nu e to the minus y minus mu squared divided by 2 nu. Great. So what do I do now? So what I'm going to do is I'm going to try to take this product and I'm going to try to convert it into radial coordinates. Then, mentioning what I said before, I'm going to draw a sample from an angle and I'm going to draw a sample from a radius, and then I will reconvert those samples into samples over x and y. Interestingly, that'll give me for free two draws from the Gaussian distribution, one for x, one for y. In principle, I should be using both because I've already sort of spent the computational effort in calculating both of them. So let's go ahead. So first thing we're going to do then is, before converting to radial coordinates, we are going to recenter. We're going to define a new variable, x prime, which is defined as x minus mu divided by the square root of the variance, and y prime, as y minus mu divided by the square root of the variance. And then I'm going to define x prime as rho cosine phi. This is now when I start converting to polar coordinates, and y prime as rho sine phi. Not sure why true. Rho sine phi. Okay, I might have referred to them as radial coordinates, but polar coordinates is probably the more appropriate term. Okay, then what I'm going to do is I'm finally going to define a new variable, and it's going to be lambda equals rho squared. So if I make these three transformations, transformation 1 to recenter the Gaussian, transformation 2 in polar coordinates, and transformation 3, we'll see why we do that transformation in a second. The integral, I should say, will depend on rho squared. So at that point, I'm going to define rho squared as lambda, just to make my life a little bit easier. And if I do that, then I find that my p of lambda and phi is 1/2 exponential minus lambda over 2 times 1 over 2 pi. Well, this is my distribution over lambda. This is my distribution over phi. So really what this is an exponential lambda with a parameter of 1/2 multiplied by uniform distribution for the angle from 0 to 2 pi with my variable phi. So what is this telling us? I can draw a sample from lambda, and I can draw a sample from phi, and then I have to undo the three transformations in order to obtain a random variable, a sample of x and y. So I draw a sample from lambda using the fundamental theorem of simulation that I talked about earlier, with lambda equal, with the scale parameter equal to 1/2. And then I draw a sample of phi. And this one, I don't need anything. I can just use my uniform random number generator provided to me by my computer, except I need to be a little bit careful. Computers sometimes ask you what the bounds of your uniform random number that you want to sample are. Instead of choosing 0 to 1, you will choose 0 to 2 pi. So try a sample of phi from the uniform, but keeping in mind that it's uniform 0 to 2 pi and not uniform 0 to 1. Well, okay, so now I've drawn a sample of lambda and a sample of phi, but I care about samples of x and samples of y. So what I now have to do is to recognize that rho is equal to square root lambda, and square root lambda is negative 2 log u1, right? This is my inverse cumulative distribution for the exponential. And by the way, earlier I had defined lambda as rho squared, so therefore rho is equal to square root of lambda, and my lambda was negative 2 log u1. My phi is equal to 2 pi times u2. So if u2, for example, is a uniform random number from 0 to 1, and u1 is another uniform random number from 0 to 1, then I can transform u2 into a uniform random number from 0 to 2 pi by multiplying by 2 pi. Similarly, I can convert my uniform random number u1 by multiplying by this term here, as given in the example for the exponential distribution, and obtain my lambda, which I can then compute a rho from. And then I have to undo the next transformation, which is that I know that x is equal to sigma times x prime, which is equal to mu plus sigma rho cosine phi, and y is equal to mu plus sigma rho sine phi. So, what have I done? I've generated two uniform random numbers. I've used those random numbers to compute phi and to compute rho. Once I have done that, I plug rho and phi into these formulas, which undo the transformation I did earlier, because remember x prime was x minus mu divided by sigma. And then I have calculated my random realizations for x and y. The method itself is called the Box-Mueller method. And the Box-Mueller method, again, is the method for generating random samples from a Gaussian. So generate two independent, uniform, random variables and call them u1 and u2. Plug them into this formula. And you are done. So you have now generated two samples from the Gaussian distribution for each iteration, if you choose to iterate more, for each iteration of the Box-Mueller method. So most computer codes, or most computer languages, I should say these days, actually allow you to draw samples from the from Gaussians directly, so you don't have to go through this algebra, but it's still good to know, sort of, because it's one of the few distributions that we can draw samples from analytically. So it's sort of, or for which we have analytical forms for C of R that we can then do this algebra on. one of the few for which we can draw samples, which actually brings up another interesting point. We've talked about drawing samples from the exponential distribution, now the Gaussian distribution, and all that somehow requires us to be able to compute sort of a C of R, or in this particular case, an equivalent, in the case of the Gaussian, an equivalent of a C of R. But for very many cases, actually, it is not possible to draw samples directly because it is not possible to compute a C of R, a cumulative distribution function, or simply called a cumulative distribution. And that sort of will lead us into discussing numerical methods a little bit later on in class. So we've discussed marginal distributions functions. That was sort of P of R1, let's say. We've discussed joint distribution functions. That's P of R1, let's say to n. There's another type of distribution and those are conditionals. And sorry, I should have called these probability densities. We've computed marginal probability densities, joint probability densities, and finally we have something called conditionals. Conditionals, as an example, are things like R1 given R2 to n. So the way I interpret this is that this is the probability density of R1 given knowledge of R2 to n, right? So I'd like to be able to determine how R1 is distributed given some other information. So just sort of saying this very concretely, suppose I were interested in this quantity. So this is rain today, and this is a random variable which considers rain tomorrow. And I were to ask the question, or I were to ask this versus that question. And here I'm asking, what is the probability that it rained tomorrow? And then you start thinking about it, you give me an answer. Well, that answer may be more refined if I ask you the question, given the outcome today, tell me what the probability is that it will rain tomorrow. So this here is a different question from this one here. Because to answer this question, this probability, you are given information which here you are not, right? So the probability that it rained tomorrow is a different question from what is the probability that it rained tomorrow given that it rained today. So more generally, we talk about sort of a random variable R2 conditioned on, so in other words, given the condition, that R1, for example, has been realized. And that's drawn from a probability distribution that depends on R1. So this is how we interpret this line here. This is saying that random variable R2 given the realization of R1 to some value R1 is drawn from P of R1. It depends on R1. R1 basically becomes a parameter in this distribution. Now, how it becomes a parameter and what exactly the form for the associated probability density is, depends on the specifics of the problems. And we'll be seeing a lot of such problems to be able to answer a lot of these questions that have conditions. But for the moment, this is how I interpret this statement right up here. So, we don't just oftentimes have one variable, we can have very many. So, we can talk about conditional dependency. Suppose that we have three random variables, R1, R2, and R3. And suppose that we want to draw samples from all three of them. What am I going to say? Let's start off very simply. R1 is drawn from some probability distribution. Now, given that R1 was realized at this point to some value, then R2, given R1, is drawn from another distribution that depends on that realization or that outcome. Now that R1 and R2 have both been realized, then I can ask, how is R3 distributed given the outcome for R1 and R2? And now this new distribution depends on R1 and R2. So when I'm drawing samples from a joint distribution, it's often convenient to be able, if I can, to write out the distribution or to write it out, to perform the sampling in this particular form. This type of sampling is called ancestral sampling. And it may be clear why it's called ancestral sampling, because I start off with R1 and I draw it from some distribution. And now given sort of the realization of the ancestor, if you want, then I try to draw a sample for R2. And now given R1 and R2, then I try to draw a sample from R3. And you're going to say, all of this is great, but how do I do this? How do I know what this is? How do I know what that is? How do I know what this is? Right? So, how do we do ancestral sampling? Well, to do ancestral sampling, you need to have knowledge of the following density, P of R1. Then you need to have knowledge of P of R2 given R1. Then you need to have knowledge of P of R3 given R1 and R2. And if you only have three variables, and these are the three things you need to know, if you have very many variables, then you may need to know more conditionals. So how do you go about learning these? Well, let's start off with what's easiest. And let's start off with what we have. So we always assume we have the joint density, P of R1 to 3, which is shorthand for P of R1, P of R2, P of R3. Again, I'm sticking to the example with 3 random variables, but in fact I could have 4, 5, or 15 of them if I like. Okay, so how do I calculate P of R1 from this joint density? Well, that's easy. We've talked about that. That's marginalization. So I'm going to integrate R2 to 3 of the full joint density in order to obtain this marginal. So I'm marginalizing. What about these conditionals? Well, we haven't talked about how to obtain those conditionals from the joint distribution quite yet. And this is, I think, something that's worth spending a little bit of time on at this point. So let's talk about it. So suppose I'm interested in P of R1 and R2. Let's start off with a joint distribution over 2 variables because that's a little bit easier. And then I can say, okay, well, how do I construct this joint distribution? I'm going to write something down, and then let's make sure we can interpret that in plain English. The way to understand this statement is that the probability of R1 and R2 is the probability of R1 multiplied by the probability of R2 given R1. Kind of makes sense, right? What is the probability that it rained today and tomorrow? Well, that's the probability that it rained today to start off with, and then the probability that it rained tomorrow given that it rained today. Now, if today and tomorrow are completely independent days, so for example, what is the probability that it rained today in Washington and tomorrow maybe in Berlin, because they're kind of far apart and maybe their weather conditions are decorrelated, then that would be pretty easy. I would write down R2 multiplied by P of R1. But in general, that's not true. That assumes that R1 and R2 are independent, which they may not be. So this, as I've written it here, is a much more general statement. And in fact, it gives us the answer to the question we wanted. How do I write down the conditional distribution? Well, it immediately tells us that the conditional distribution follows by dividing the joint with the marginal. And how do I obtain the marginal? Well, I obtain the marginal by marginalizing over the joint distribution. So at this point, I have expressed my joint distribution, my conditional distribution using a joint distribution and a marginal of a joint distribution. So all I ever need to know is my joint distribution. And from the joint distribution, I learn the marginals by integration and the conditionals by division. Okay, you're going to say, oh, that's great, but you had given me the example with 3 random variables. So I had P of R1 to 3, and to perform ancestral sampling, I needed P of R1, and I also needed P of R2 given R1, and I also needed P of R3 given R1 and 2. How do I construct all of those? Okay, well, let's do it step by step. I have, or I assume that I have, the joint distribution. Then P of R1 I obtain by marginalization of 2 variables, 2 to 3, P of R, 1 to 3. So far, so good. Okay, then how do I obtain P of R2 given R1? That doesn't look so easy. Well, that's going to be P of R1 and R2 divided by P of R1. And you're going to tell me, oh, that's great, but I don't have P of R1 and R2. But you do, by marginalization over R3. So you've noticed now that I've been able to express the conditional of R2 conditioned on R1 as equal to the integral over R3 of P of R1 to 3 divided by sort of this marginal d of R2 to 3 of P of R1 to 3. And now we just have one calculation left. P of R3 given R1 to 2. How do I do that? Well, that's going to be P of R1 to 3 divided by P of R 1 to 2. P of R 1 to 3 is already my joint distribution. I don't touch that. And P of R 1 and 2 is simply the marginal over R3, P of R 1 to 3. And this is how I start off with my joint distribution over all 3 variables, compute my first marginal, my first conditional, and my second conditional in order to be able to perform ancestral sampling. So, to summarize a little bit chapter 1 so far, let's just talk about kind of what we said. We've talked about probability distributions. We've talked about random variables. We've talked about examples of sampling of random variables. We've talked about sampling discrete random variables and continuous random variables. In the case of continuous, we sort of dealt with a slightly more complicated case of the Gaussian by Box-Mueller. And finally, we've talked about sort of how to relate marginals and conditionals and joint distributions to each other. So joint distributions are always the distributions that have the most amount of information, and marginals and conditionals are constructed from the joint distribution. So all of the information you would ever want to have is in the joint distribution, but it may be hard to sample from the joint distribution. Maybe it may be easier to sample from this, or that one here. So when I have to draw samples of 3 random variables, it may be convenient to use ancestral sampling in the way that we showed here. Sample P of R1, then P of R2 given R1, then R3 given R1 and R2. And we can show sort of, and we will deal with specific examples of that as we go along.